All right, welcome everyone to the third lecture on an introductory lecture on scattering amplitudes and Feynman integrals. So again, let's pick up from where we left off last time. So last time we finished discussing the spin or helicity variables that allow us to conveniently describe both the momentum and helicity of massless scattered particles and trade them with these spinor variables, lambda and lambda tilde. And in particular, in the previous lecture, we discussed how helicity is also encoded as a phase in these spinors, whereas previously we had discussed how momenta is described by them. After this, we moved on to discuss how one can remove essentially the color degrees of freedom of scattering amplitudes. If you scatter colored particles, gluons or quarks that yes are charged under the gauge group, under the yes of your gauge theory, then you also have these indices coming with generators of the gauge group, and we discussed how it is possible to disentangle these, to factor them out, and then to be left off with an object known as the color-ordered amplitude, which no longer depends on color, and it's therefore much simpler. And after so this is the focus I then focused on for the rest of last week's lecture, and I went on to describe how we can compute it. So it's this one that we will try to compute. We try to compute at 3 level, not with Feynman diagrams, but with the so-called Britto-Cachazo-Feng-Witten recursion that exploits the analytic structure of amplitudes, one of the themes of these lectures. And how did we do this? We introduced a single complex variable in a very particular way by shifting the momenta of two adjacent legs. You can pick anything you like. I picked 1 and n. And so we have that, you see, z enters by shifting one of the two momentums, of the spinors of particle 1, and then the other momentum twist, or the tilted one of the other particle, with a different sign. So linear deformations that also preserve many of the properties of the original amplitude. The momenta are conserved, the masses, the external momenta squared are 0, the particles remain like. And then the essence of BCFW recursion is to look at the analytic structure of this deformed amplitude that now depends on Z. And it's not hard to see, to realize that this object, especially with respect to Z, it has poles. How does one see this? One sees this, for example, by drawing Feynman diagrams that might contribute in the process. So this is a 4-gluon scattering, and you have a 3 level. So we're talking about 3 level scattering amplitudes. You have some interactions. You see here you have particles 1 and 2. This propagator will have momentum P1 plus P2 squared. And if the values of Z that enters over here, are such that this sum of Mandelstam of momenta vanishes, then this diagram will have a pole, as you can see here, 1 over. So this is a 1 over P1 squared, capital P1 squared pole. And I mentioned this last time, but let me also bring an example of a Feynman integral. You only have particles that are ordered and no lines cross each other. So, for example, this is this kind of graph where you have this called U channel, where you have these lines crossing, is eliminated by color ordering. That's why the poles are not with respect to any sum of momenta, but only with respect to adjacent momenta. And okay, these are some particular examples that allow us to figure out the general picture, which more generally has to do with looking at all these consecutive poles of the amplitude with respect to z. This is all the possibilities that contain z, where I goes from 3 to n minus 1. Why from 3 to n minus 1? Because in order to have scattering, you need to have the left and the right side to have at least 3 legs attached to them. And this is the same statement that I showed you before with the particular Feynman diagram. And the amplitude is the sum thereof, so it will also have poles of this sort. What is slightly more involved, but one can also try to show, is that in this case, the amplitude also factorizes. The Feynman diagrams conspire and factorize in these forms so that you have left and right. They have partial amplitudes with fewer legs on the left and the right hand side. One of the things that you asked about last time is how come this p square is linear in z. So maybe, would you like to see this, or you tried it out, you believe me? I think you asked. Would you like to see why is this the case, or shall I? No preference? Okay. So then I will skip it, but all right, it's a small calculation to show that p hat, capital P hat squared is capital P squared without hat minus z, and this object, which is just defined as lambda n, sorry, lambda 1, yes, lambda n alpha p I alpha alpha dot lambda 1 alpha tilde. And okay, I can very briefly say that essentially you get to multiply, yes, the piece that goes as z squared turns out to be something like 1 spinors, and then n bracketed spinors, and this is an antisymmetric object, it vanishes. So the z squared piece vanishes, and you are left off with something linear, as you can see here. So in fact, we will have simple poles, not just poles, but simple poles. And then, given that we have these simple poles, we obtain the original amplitude, so an where z equals 0, from Cauchy's residue theorem, where we have that an z equals 0, what we started with, is 1 over 2 pi I dz by z a n of z. So the default amplitude has no pole on z, so this is the only pole it will pick up, and the contour over here is this little contour that goes around 0 counterclockwise. So This is clear for everyone, right? A simple application, of course, is reduced theorem. And then by deforming the contour, so if we deform now the contour, so deform contour to infinite radius. So if we keep increasing the contour, we will have poles too. So we do have poles uh, at these locations when this combination vanishes. These are the ZPIs. And so we will also pick up these contributions, and we need to subtract them if we are considering the big integration contour. The sum of whatever it contains will be this amplitude plus the residues that we pick up from elsewhere. And so this is, let's see, all right, I can write it. In any case, this will be intermediate formula. I'm repeating some of the things we discussed last time. And then I squared, then AR. So this is really from, yes, the contributions around these poles. This is from this formula over here. You really pick up so you take the residue. The residue will essentially be this bit and this bit. And this is what this formula tells you. And then you also need to be careful, because when also are at infinity, you could also have a residue. And the final formula that I will write down and pause if there are questions. So assuming that this residue is 0, and we'll come back, we'll revisit this. We have the BCFW formula that tells us that AN, this is now the undeformed amplitude, the original amplitude we started with. This has to do with the number of poles with summed. This has to do with the fact that we have on-shell particles propagating between the two subamplitudes, so we have to sum over all, it's quantum mechanics, over all possible degrees of freedom they have. And then we have that the left side, okay, depends on particle n hat, so also on this ZPI, so this is the pole that we are considering. You have minus the momentum P, because you are in the convention where everything is outgoing. So this also depends on CPI, capital PI squared, and then the right hand side, H I n minus 1 n hat, again, ZPI. And I just reiterate that the capital PI is just the sum. And also this ZPI is essentially, you factor out this piece over here, and this tells you what is the value of z on the pole. So this is the celebrated BCFW formula that we arrived at last time. And what I stressed, and let me stress again, is that, okay, so this is the BCFW recursion. Because if you know if AI where I is up to n minus 1 is known, and this would be, let's say, the right-hand side, then also AN is known, is determined, computed. And this would be the left-hand side. So the essence of this and the beauty of this is that it's a recursive method that allows you to build and build more complicated scattering amplitudes strictly from other scattering amplitudes. So it's completely on shell. Nothing on the right-hand side is off shell. Everything is on shell. So there is no issues with gauge invariance or redundancies because of, yes, choices of gauges, gauge dependence, exactly. So this is, yes, the outcome of really relying and exploiting the analytic structure of scattering amplitudes. So this is, yes, summarizing and yes, recapitalizing on what we did last time. Are there any questions?
So, I mean, this relies on the fact that you can make one possible cuts. I guess it's just three.
Mm-hmm.
Yeah, that's true. Sorry, that's the question. That's true. It's restricted to three
So you can always cut a diagram in two pieces that usual unitarity. That's the like old school unitarity, and this is possible. But you are right that this like method is very constrained to three levels. Also because the analytic structure is just folds. I would say that's how I would phrase it. Yes, exactly. And this is what I will move on to discuss today later on. More questions?
When you take the rises to infinity, you should get vector equals all the residues, but then you move one of them to the left-hand side. My question is, why do not minus residue z equals
Uh, it could be. It will be. Could well be.
so taking another integration formula.
Yes. Yes. I was mostly relying on the yes on Sagex review chapter 1, and okay, there was a plus sign there that I didn't think much about, but you are right. But well, it may have to do with the fact that, okay, what is the residue at infinity? You take, let's say, your variable and you invert it. You take z to be, so w to be 1 over z. And then this might also introduce some extra sign when you do this. If you differentiate, you definitely get an extra sign. So there are some, yes, like some signs. Yes, I have many signs in my office. Whoever wants some can come and find me. So in any case, this will be 0. So let's not worry too much about it. But I agree that if one wants to be completely rigorous, one should revisit this and really, yes.
Pick another minus sign for the sign, and then and that minus sign cancels out, right?
Sorry?
You must have all the residues on one side the sum, right? Should not be a minus sign between them as well.
Here you mean?
Yeah.
This has to do with, no, this is correct. The sign has to do with also the like, yes, the, the, the direction of the integration contour. Well, you see over here you have like ZP minus Z, so you get an extra sign here. So that's why in the end, this is the correct sign. So this, I can vouch for that sign, I can vouch. For the other one, no. But we can discuss it later. More questions? Okay. So then let's come to discuss. Yes, let's come to the main dish for today. Since I had to spend a little bit more time on this, since I had to rush them last time. Yeah, let me. So okay. So this time, what will we do? We will, okay, continue a little bit BCFW in the following sense. We will first discuss how to seeding the recursion. What's your starting point? Okay, you have a recursion, but what's your starting point? How do you really apply it in practice? And then the second thing will be, again, the pole at infinity. To come to discuss this, at least briefly. And then we will move on to some loop level technologies. All right, so let's finish with yes, the complete story. Let's complete the story of BCFW. I will not. Yes, I will try to give you the tools you need, the information you need, so that you can then try it out. Try to compute some amplitudes by yourself, if you'd like, and get some exposure on them. So, seeding the recursion. The seed are the 3-point amplitudes. Perhaps no surprise, we said we need at least 3 particles to have some kind of scattering or some kind of decay. And our deformations for BCFW in any case make some of the momenta complex. So we can think about complexified momenta in general. And we will have in particular that some of the amplitudes are 0 no matter what. Whereas some others, at least if you are thinking about complexified momenta, and so then we have 1 plus, 3 minus, which is very similar. Okay, it has an extra sign, but other than that, out of conventions, our choice of conventions, but other than that, it's like changing brackets, angular brackets to square brackets, or if you want, it's like complex conjugating in some sense. So this is so-called the maximally helicity violating amplitude, or MHV, whereas this is the anti-MHV, or MHV bar. And unfortunately, I will not have time to present this today, but it turns out that this fall can be determined completely from a symmetry locality. So So again, in a sense, we don't need again Feynman diagrams to figure this out up to this overall constant. Okay, here the overall constant turns out to be 0. But symmetry and locality takes us a very, very long way. And this is, you can, if you are interested, you can find this in reference 6 in section 2.6. I think this is the book by Elfang and Huang. And you can also read this if you are interested. But in any case, these are our building blocks. This is what we will start with. So let's say try to compute the 4-point amplitude based on these building blocks with all possible helicity assignments. And maybe I can provide, yes, some exercise. Or let me ask, would people like to try out their luck on this? Shall I suggest something for you to try, or you're not planning to? Okay, let's do it. Just in case, yes, you would like to go on with theory, but all right, let's have this exercise. So use induction and BCFW over there with this building block to prove 1, that amplitudes with all helicities the same are equal to 0. So in a sense, what we saw here also generalizes to any particle number and can be shown. So this is an all n. That's also an interesting, very interesting feature. You can really prove all n results with these methods. Then you can also show that, let's say, the ones with all but one helicity is the same is equal to what's that? Sorry. I had 3. Sorry. Please forgive me. N. Where n is greater than 3. Very good. So some of these are precisely of this flavor. You really split things up, and you see that no matter what you do, you will always have, say, a 3-point all plus piece. So this has to vanish. There's no other way. So some are, yes, very beautiful and very simple. And finally, let's say 1 minus 2 plus and minus 1 plus and plus minus. Okay. So sorry for writing here. So let me do it better. So this is I times g to the n minus 2 and 1 to the 4. That's the numerator. And then the denominator is the product. 1, 2, 2, 3, and so on, up to n1. All consecutive angle brackets. So,
Question about the NHD you said that fixed subtotal constant. Is that just one constant between both, or two constants?
that's an excellent question. What do the audience think? What do the students think? Yes, why?
Because of like conjugation.
Yes, that's. Do people agree or disagree? Agree. Yes. Very good. It's actually parity that yes relates them. But parity, if the momenta are real, corresponds to indeed complex conjugation. So, but more generally, yes, they are related, and therefore it should be the same constant. Very good question. Thanks, George. Mm-hmm. Yes. So we are really discussing, yes, gauge theory amplitudes here. Scalar amplitudes, yes, they have been, these methods have been applied some by adjoint, or yes, some scalars that are also, so Lorentz scalars, but have also some gauge, like some gauge group dependence. So yes, some trace phi theories. So whether these apply to scalars that, yes.
In a sense, they can, in representation of Lorentz, which is zero helicity, means it's possible.
Yes.
But still, momentum can split Landau when it's found.
Mm-hmm.
So in principle, I can either do zero or still use that formula, but which one?
So it should be a massless scalar.
Yeah,
So that's a bad idea. And that's an interesting question. For sure, okay. These methods, okay. These methods are also secretly supersymmetric in the sense that if you are looking at 3-level amplitudes, it doesn't matter. So if you have, let's say, pure gluon amplitudes, they will be the same in a supersymmetric theory or in QCD. Because it's the same particle, everything is on shell, they are the same. In these supersymmetric theories, you can also relate these amplitudes to amplitudes of scalars and so on. So this is possible, and in the end, one can show that there is a number of independent amplitudes, and every amplitude, let's say, probably one can pick the gluon amplitudes, and then the scalar amplitudes will be certain linear combinations thereof. So.
Let me ask you a question. You need the amplitude to the scale. That's why you can't have all these same lists of states. But in the scale of the field, naturally scale. So what's the answer? Is it zero or it's certainly not zero? It's
Well, you need to specify an interaction also for your scalar particle. G, but is it phi to the cubed? Is it phi to the fourth? So we are now talking about gauge particles which have a very well-defined Lagrangian.
Which will I use?
Okay.
No, but my question is very basic. So if particle was in helicity, which means they have just raised pluses and minuses, right? Then all this MHV doesn't make any sense because there's no helicity.
So is G specifically the gauge interaction? And again, the scale particle wouldn't have that at all. So G would be 0 for the scale particle. You could use it.
Sure. Also, series and against series, sure. But
I agree with this, and well, you know that if you phi to the fourth to lead in order the four particle lines is just the vertex, the four particle vertex. If you have phi to the fourth, so exactly.
anyway, so punchline, this is not really applicable.
Yes. As such, only if supersymmetry relates this gauge theory amplitude, this gluon amplitudes to scalar amplitudes. Exactly. All right. So try and give it a go. This is fun. This is fun stuff.
Why did it should one of those be one n and one, the other four and
Well, this is to the fourth, so it doesn't matter. To the fourth power.
okay, but you divide it through
1, 2 to 2, 3 to 3, 4 up to n 1.
Yeah.
This is always there in whatever. So this is the n particle MHV amplitude. So n particle MHV. And okay, this is the formula I presented in my very first lecture. Okay, there it was slightly more general because here I picked particles 1 and n to be those of negative helicity. One can have one can pick other ones, and this numerator will change. It will select those that have the negative helicity. And these MHV amplitudes, as you see, are the first non-trivial three-level amplitudes, the first ones that don't vanish. And they don't vanish, but they have a very interesting feature. They're purely holomorphic. They only depend on the lambdas, but not at all on the lambda tildes. You see, only angle brackets, no square brackets. All right, and to conclude with BCFW, I will erase this beautiful formula now, sadly, but let's come back to the issue of how this deformed amplitude depends when you take Z large. So behavior of AN Z as Z goes to infinity. And you can show, so I will just quote this. I will not prove it due to lack of time, in the interest of time. But the result depends on what kind of helicities you pick for the shifted particles. Then you can show that this behaves as 1 over z. And the same is true also if you have the same helicities, again, and also if you have minus helicities. Also. So remember we had an integral, yes, from residue theorem, we had something of this sort. So this is 1 over z squared. And so this indeed behaves well at infinity. It has no residue, no simple. It's higher than the simple pole. It dies off. You see that dies off when you take z to infinity. There's nothing left, and so these are allowed. So these are allowed shifts, and the first one can show relatively easily from color ordered Feynman diagrams. From color ordered Feynman diagrams. So it's a matter of, again, following the path of helicities, yes. And it's, one can see that there isn't much choice there, and this is the only possibility. The other two are harder to show, but for the other ones, see, for example, 08, 01, 2385. So these are harder to show. And there is also an outcast. Let me, yes. So not all goes, not everything goes. And then if you try the one minus n plus, and z goes to infinity, this goes like z cubed. And so this is forbidden. You cannot assign this type of helicity. Of course, this is not really a deterrent because you will definitely have two or more helicities to be of opposite sign. So it's a matter of simply picking, yes, the adjacent particles with which you will do the shift. It's a matter of not getting the wrong answer. But it's, yes, this is, this requires some quite detailed analysis, and you see it came about much later, in fact, than the original story with BCFW in 2004. Okay, that was it with tree-level BCFW. Anything you would like to know?
How I'm maybe a bit surprised that you can see the whole recursion with just 3 points. Like the 4 points seems to have been completely fixed. And I think that maybe this is from gauge invariance. I haven't formulated this as a question.
No, no, well,
I'm just surprised that.
When I said seed, I mean from this you can get the 4 points.
Yeah, I'm maybe surprised that you can do that.
But surprise in the sense, okay, so the BCFW formula certainly allows you to put n equals 4 on the left-hand side, and then decompose it in terms of 3 particle amplitudes. So what is the surprising aspect, if I may?
Maybe, so I think maybe the 4-point vertex is fixed by gauge invariance, by the 3-point.
The 4-point, yes, of the gauge theory, yes, agreed.
And maybe I've forgotten where BCFW forces gauge invariance, because otherwise it seems like I could have set, suppose I broke gauge invariance and I put in a different 4-point vertex. BCFW then doesn't know about that. Like that 4-point vertex being different should change the result. It's maybe a new point because I can't change that 4-point vertex because it's fixed by gauge invariance. And maybe I'll ask you later to say what I'm asking better.
Okay, let's discuss it then in the break. And in fact, it is time for a break now. But let's see if there are more questions.
Can you use the same for gravity?
You can, so this is tree level. There are nice, like relations where gravity amplitudes are the square of like gauge theory amplitudes, yes, stemming from string theory. So this you can yes, it takes some work. It's not well. No, from string theory you can motivate why this is the case, and then you can take the field theory limit, and at tree level it's kind of yeah, it's derived, so to speak. More questions? These are the KLT relations, Kavai level and time, by the way. All right, then let's take a break. It took longer than anticipated, as always. But hopefully it remains interesting, and stay tuned because after the break, we go into loops. All right, so in the next hour, let's move to the next chapter that I was hoping to cover. So, loop technologies. And for this, we will focus now not on scattering amplitudes, but on their building blocks, Feynman integrals. And let me give you a short status of where we are currently. So, status of amplitude calculations and their methods. So, when we are at tree level, as you already saw in the 2.5 lectures we already have, the story is solved. Because you have either this BCFW or some Behrens-Gille, also alternative, but in any case recursion, so alternative methods that are recursive and allow you to, yes, build more complicated amplitudes from simpler ones. Moving on to one loop, it turns out that this story is also solved. And here, the main line of attack is called generalized unitarity. By Bern, Dixon, Dunbar, Kosover, etc. I will not talk about generalized unitarity in this set of lectures because it is not currently the one loop is already solved. So it's better also for interest to expose some more yes, recent technology and things that are active. There is active research on at the moment. So if you go then to two loops and higher, and I repeat, these are warranted by experiments. So for experiments, you need them. There is this, for example, Lesuche wish list of experimentalists where they ask, I don't know, what amplitudes could you compute as theorists, and many are at two loops or higher. And this is the ongoing effort. And unfortunately, there is no general method avoiding Feynman diagrams. So if you want the generalized unitarity, avoid them to a great extent. But at two loops and higher, currently, you cannot avoid using these building blocks. And that's why precisely we will focus on them today. Just to try to keep the discussion as simple as possible rather than summing them all up, just to consider them individually. And okay, what are the complications that show up at loop level? Maybe I should also say that use 3-level lessons though, 3-level lessons. And this is hopefully that analytic structure the knowledge of the analytic structure helps a lot. Very helpful. So let's try to understand what is the analytic structure of Feynman integrals. And the first question we would like to ask when we talk about analytic structure is what kind of singularities do Feynman integrals have? So there was already a discussion earlier on, and one of you also asked a very relevant question. So what's the main difference between 3 and loop level? So at 3 level, we saw that we could have algebraic singularities, namely the poles. We saw that amplitudes had poles in in Z because we introduced this variable, but they definitely have poles in the propagators that are shown in Feynman diagrams. How about when we introduce loops? What happens? Do you just get algebraic singularities? Do you just get poles? Do you get something more complicated? Yes, logarithmic singularities. So indeed, this you can see very easily. So just let's be physicists and let's try to very roughly have some kind of tadpole diagram, just a single propagator, but now you integrate over it. And then if you go to polar coordinates, it's something like p cubed dp. And then this one can easily do and find something like so this is just, the fact that you have, we did it with the propagator, you have 1 over x, you have some poles, and then you integrate over x, will inevitably get some logarithmic singularities. Exactly. And then the next question we can ask is, where are these singularities located? Okay. And for this we will answer them with a toy example. So answer for a toy example. Let's take a 1 variable integral, so 1 integral with 1 external parameter, which we will call z. Okay, so let's take our function fz to be given by an integral over some curve gamma ab, and let's take it to be of this form. So there is some integrand that depends on both the external variable and the integration variable. And this is also the contour. So this is A, this is B, so this is the contour gamma AB in the W plane. Okay, and we can also, in full generality, since we have, oh no, so not in full generality, sorry, and let's also, again, to keep it simple, but also similar to Feynman integrals, where g of z, the integral, is a polynomial. Let's write it R1 of R1 of z up to Rm of z, sorry, minus W, dot, 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 M of z minus W. Namely, it's a polynomial in z, with, sorry, polynomial in W with z-dependent coefficients. I just, since it's one polynomial in one variable, it's a fundamental like theorem of calculus that you can factor all the roots. That's all that I'm doing here. Okay, polynomial in W with z-dependent coefficients, the external parameters. So let's, and all right, so these are the roots of the polynomial. So roots, these are the roots of G, and so what do they give for the integrand? When you are at the root of G, what happens to the integrand? Sorry? Yes, it's a pole of integrands. So let's say that, okay, here you have R1, and here you have R2, and so on. Okay, now let's assume that a single pole, so this, and this move as you say, change z's. So this move as z varies. So because they move, I dial z around the variable, and it might so be that one of the roots of this polynomial go on the integration contour. What happens then? What's that?
Well, I mean, it depends from which side you look. And then, well, there will be a jump.
There will be a jump if just one pole approaches. Do people agree?
What do you mean by jump? Well, because you can approach from the left or from the right, and then the value will be different. The both finally will be different. And different by the, well, it's supposed to form.
I beg to differ, because if you, what's that? Yes. So the deal is that if you just have a single pole approaching, you can always deform the contour. So let me say this: single Ri approaching contour. What you can do is that you can deform to avoid it. And so this is, an analytic continuation of your function. And it turns out that because you can do this, then f z is non-singular. So therefore, f to z is non-singular. So all I am saying is that, let's see, let's pick a color. Let's pick this color. So I deform my contour smoothly, and so I avoid this. And then this kind of analytic continuation, choosing another path where you have not crossed any poles, is really, yes, extending the domain of validity of your function. And nothing is wrong. It's like extending, yes, the gamma function by relating it to the function with one, like, so gamma n is gamma n minus 1 divided by n, and so on. So no problem. We can, this is no issue, no singularities appear. Now that we have discussed this possibility, can one tell me what are then the real possibilities or the actual cases where this function develops singularities? Very good. And okay, in my note, I have this as the second possibility, so I write it as 2. You have that Ri, let's call, I don't know, Z1 for some value of Z equals Rj of Z is some interior point of the contour, gamma alpha beta. So in this case, it's okay if I erase this scenario. You can always, in your notes, make a new. So I will cheat and I will just erase this, but you can make a new drawing where now both poles approach from two different sides. There should be, but yes, and then they collide. They collide right on the contour. And when this happens, there is no freedom. You cannot move the contour. You cannot deform it and analytically continue your function to avoid the singularity.
Do you agree that in your case it doesn't matter whether gamma e close or open contour? In principle, to be solved, right? For the second argument.
To be what, a circle? I would have to think if there are differences, but
Okay, imagine it's just real line. Just real line. And we have R1 going from the top to the bottom. Of course, that you will analytically continue, but the value of integral will jump. Now, it's in the case of a single pole. Now, if pole is double, you just different shape. And of course, then you will calculate most of its similarity. So that's what you're saying.
mm-hmm. Yes, you can analytically continue your function. Okay, you might have a multivalued function. Maybe that's what you were saying. But I was really talking about singularities in the sense that, yeah, the function is not defined there. Well, yes, yes. So we agree with this. Very good, excellent. Other possibilities? Surely there's one more, if I have two. Excellent, excellent. So when Ri goes to A or B, because the endpoints are part of what you have defined your integral to be, and you cannot move them, so can't move endpoints. So this would be, again, I will use the same drawing over here, but hopefully you already took notes, and you can have something like this. And then you, again, might, it depends what the numerator is. Here we have no numerators. Here you will most definitely, well, could be integrable, but it's a potential singularity. You might well have a singularity of your function. So therefore, necessary conditions, so not sufficient. Indeed, you might, in general, have some especially if you have numerators, some numerators could cancel the singularities. But from this analysis, we find that the necessary conditions for Fz to develop a singularity okay. The first equation, and I had this I and 2I, but okay, maybe I should distinguish them. All right, forgive me, let me call them 1 and 2 so that you don't get mixed up with the equation. So equation I, so in all examples we saw, what happens to G, to the denominator? Goes to 0. So this is definitely a necessary condition. Otherwise, what singularity are we talking about of the integral? And then the second condition, all right, let me start with, all right, how will we, can one see how we will express the fact that two poles collide? How would we express this? What's that? The derivative is 0. Very good. That's what the higher order pole means. Sorry, higher order root of the polynomial. Okay. So that takes care of this case where the contour is trapped at its interior. And then you also have the possibility that you are at the endpoints. And this is precisely, as Sasha said, this tells us that we have a multiple root. That exactly, these two factors, let's say, coincide, that R1 becomes Rm, and so you get a square, and therefore also the first derivative vanishes. And whereas these have to do with the endpoints. So with this toy example where everything is kosher, everything is very straightforward, and we can follow the steps, we can get inspiration and we can move on to discuss singularities of Feynman integrals. And what we will discuss are the Landau equations. I write also. Indeed, introduced by Landau in 1959. And these are nothing but the multivariable generalization of our analysis, our simple analysis, where one is particularly thinking not about, okay, any integrand, but how the integrand of Feynman integrals is in particular. So for this, we will first write down what the L-loop integrand looks like before we can also state the equations. So the L-loop scalar graph with n propagators big N, capital N, and n external legs takes the form I equals product of loop integrations where D is the dimension of the loop integration, as you see. One could at least naively think of it as 4. We will come back to this, but it's best to keep the dimension as a as general, where this is also some normalization. So it shouldn't bother us too much for now, but this is a convenient normalization where gamma E is the constant. And the epsilon, okay, well, I write everything, I guess. Okay, I come back to this. D is D0 minus 2 epsilon, right? Yes. Okay, and then I come back to this, and then we have the propagators. So qi squared minus mi squared plus I0. And okay, this is the causal prescription. This object has a pole right on the integration contour, okay, which is, yes, R, sorry, it's Minkowski, yes. So, yes, from minus infinity to infinity in Minkowski space. And these are the masses of the propagators. And then Q is also the momentum carried by the propagator. So Q, you can write in general as a sum of the external momenta, A or alpha ij, kj plus beta ij, pj, where alpha and beta just take values 0 and plus and minus 1. So these are combinations of the internal loop momenta and the external momenta. Okay, you also have momentum conservation. And all right, I already wrote this here. We work in dimensional regularization. So this is, yes, dimensional regularization. because integrals, if you stick to really the 4 dimensions that our world, our universe is, our objective reality lies, these objects are not also well defined. They diverge. They can have infrared or ultraviolet divergences. If, let's say, there are many numerators here, then when K goes large, this thing will blow up. If there are many, let's say, propagators down there and no masses, then when P goes to small, this will also be like that. But if you go to away from the integer dimensions by this epsilon amount, you regulate this divergence. So this is the 't Hooft-Veltman dimension regularization. People are hopefully familiar or have seen this before. Okay. And for our purposes, yes, this will be a positive integer, d0, positive integer, mainly 4. Okay, so these are the objects we will focus on, and anything that is unclear in this very general form that Feynman integrals have. And shall I give a simple example just to make it concrete, or you're fine? Simple example? What's that? Okay, so example. One loop, uneven mass bubble. It's in fact something that I will use also later on. So this is, I write proportions so that I get rid of this, so that I don't write, just so that I'm a bit faster, sorry, D. Okay, pi over 2, 1 over k square minus m1 square, k minus p square minus m2 square. And this is just our beloved bubble. So this is minus p. This is m1. Yes, m1, m2. This is q1 equals k. This is q2 equals k minus p. But okay, we have it like momentum integration at its vertex and so on. So it's really of the same general that I wrote down over here. And what we will do next to try to, so what's our goal? To write down the analog of these equations, the Landau equations, for Feynman integrals. And to do this, we will, so I take the example aside, and so we will introduce Feynman parameters and this can be done by generalizing the Feynman trick that you have probably seen. You must have seen in your, so generalize. It's the trick of taking a product of two denominators and writing it as a single denominator. So from 0 to 1, the alpha A plus 1 minus alpha B squared. So you can apply this, for example, over here to bring everything in one denominator. So this is the Feynman trick, and you can do it also with many products and so on. And therefore, if you do this, then our previous definition for a general Feynman integral becomes, okay. Again, I just wrote proportional to avoid writing the normalization factor. D K J I T T over 2. So you have to, okay, if you've seen it, you've seen it. If not, you will have to believe me a little bit, but only a little bit, because already by this kind of story, you can apply, you can already get, let's say, this general form applied to the bubble integral, essentially, with this formula. And okay, instead of having alpha and 1 minus alpha, here you have a delta function enforcing, yes, that one of them, let's say, in this case, alpha 2 is 1 minus alpha 1. So this is the, what's that? The product here, you have as many alpha parameters. Where do I, for the alpha I, sorry. The alpha I, thank you. Yes, very good. Yes, yes, the integration variables, thanks. Yes. The denominator, is it, I guess, what's that? I, yes, this I goes from 1 to n capital, which is the number of propagators. You have as many Feynman parameters as you have propagators. Yes. And then once you get there, then, yes. Yes, that's true. Yeah, yeah, I might have missed this, and oh, sorry, that's yours. That's yours, that's mine. Good question. Yeah, like naively, you're right, it looks like 2. One, yeah, I can't quite remember because it's, can also write down um, the general propagator pairs, and then there is definitely. Mm-hmm. Yes. To the end, you're right, to the end. That's it, yeah, to the end. Indeed, and that's 2 because over there you have 2 propagators. Very good. Thanks for being observant. Excellent. Okay, so this whole thing is to the end. Okay, so now we have like an integral that very much looks like our simple example. Okay, there's a delta function, but other than that, there's a single denominator. And therefore, this is what the Landau equations are. The analog of these equations for this particular integral. So I can erase, can I erase here? Okay, so the Landau equations. They are conditions for the I as to become singular. And they are very, very analogous to these ones. You have either qi square equals mi square or alpha I equals 0 for all I. This guarantees that the denominator is 0. So it breaks apart this relation. It's the analog of this relation. It's demanding that this whole object is 0, but you break it apart. For this to be 0, it's a sum. Every single term has to vanish, and either this bit or this bit have to vanish. And then the second condition is that for every loop L, so you have that alpha I qi of nu equals 0 for all L equals 1 to L. And this is essentially, if you wish, it's the propagator differentiated with respect to k. It's the propagator is just quadratic, or the inverse propagator. And okay, this so it gives you a single power of q, assuming here that okay, it's a matter of convention that that q equals k plus dot 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 to just avoid proliferating some extra signs. If you had to be q to be minus k, you would have a minus over here. So just this equation. So this also takes the form of a total derivative, of a derivative with respect to q. So these are the Landau equations. And it's clear, I hope, from the exposition that they really follow by working a little bit harder than the one, the single variable example we discussed. So this tells you where the singularities of Feynman integers are located. These are the equations that were derived, as I said, long time ago, but still remain, for reasons I will hopefully explain, at the center of very vigorous investigation. And there was also a conference in Edinburgh, Frontiers in Landau analysis. So there is lots of activity on computing the Landau singularities of Feynman integrals. Questions?
Can you explain one more time where you get the second term?
Second equation is similar to also differentiating the denominator. So this is the denominator, and you differentiate with respect to the integration variable, which is k. So it's roughly differentiating this with respect to k, and okay, if you differentiate the whole thing with respect to k, only the q's that contain a particular k will survive, and that's why you have the sum over loops over here. And since each piece is quadratic, you differentiate, you get a linear term in q. That's where it comes. More questions? Okay. Then let's do an example. Let's come back to this integral and try to compute the Landau equations for them. So I guess I can keep the equations. I can erase this. Now that it was for us to motivate and understand, at least conceptually, by analogy, the Landau equations, so that they don't come out of a hat. It's a rabbit out of the hat. Okay, so let's go to this example and let's compute the Landau equations. Let's solve. Let's write down and solve the Landau equations. So one thing we could do in the beginning is we can contract the second Landau equation with qi mu for every, so for I belonging to a particular loop, the one that also appears in the equation, so loop L, and then, okay, again, we have all the different loops. But if you take and dot this object with, yes, I should say Qj, let me say Qj. So you dot with respect to the Lorentz index to build the Lorentz scalar, and you take all the possibilities that also appear in the sum. So therefore you will get a matrix. So you will get then, so let's call this 2 prime is Q alpha vector equals 0, where Q ij, so Q is a matrix with has indices I and j, elements I and j, and are just the products of Qi and Qj. And then alpha vector is also a column vector, which simply has the individual Feynman parameters as components. So I just dotted it with all possible Qj's that are a single loop, and this depends, so this is different. This is Q that depends on L for every loop of the diagram. Okay, here we just have one loop, so we will have one Q. But this is just a rewriting the equations. And since you have that Q1 equals K, Q2 equals K minus P, in this example, you can, all right, you know what the Q1 and Q2 is. And let's now try to consider the different cases of solution. So let's consider the cases where both alphas are different from 0. Then over here you have, different branches of solutions, different cases of solutions. So let's assume that all the alphas are non-zero, namely that the propagator is on shape. You have that Qi squared, I squared equals mi squared. And since this is a homogeneous equation, so homogeneous, what is the condition for this equation to have a non-trivial solution? Namely, not one that alphas are like identically 0. Both alphas are identically 0. Excellent. Because it's homogeneous, that Q, which is equal, all right, this is Q1 squared, it should be equal to and here you have Q1 dot Q2, Q1 dot Q2, equals 0. And therefore, Q1 dot Q2 is plus or minus M1 dot M2. Then what you need to do is recall, okay, just look at these equations. It's clear that P is Q1 minus Q2. Let's square it. So this is Q1 squared, this is M1 squared, minus 2 Q1 dot Q2, minus M2 squared. And if we plug this in over here, we find that P squared is a 1 plus minus, I guess minus plus, yes, M2 squared. So that's one of the solutions of the Landau equations, where both alphas are not zero, and can also compute the alpha i's. Now that we have these equations, we can also find what the two solutions for the alphas are. And I encourage you also to try this. So. All clear? All right, then let's look at the other case. How are we doing on time? 5 minutes. All right. So then the case where let's see, which one did I pick? Because there are two that are related by symmetry. Okay. Case alpha 1 is different from 0, and alpha 2 is 0. And this means that in this case only Q1 squared by the first equation equals M1 squared. And also, all right, then we look at this equation. One of the alphas is 0, the other one is yes. For the other Q1 is M1, so we have alpha 1 dot M1 squared is 0, and this gives you very simply that M1 vanishes is also another Landau singularity, and similarly for alpha 1, alpha 2, M1, and 2. Here can also compute, one can also compute, well, it's in this case very simple. I think you can see it, right? Yes, okay. Well, you can see it remembering the delta function. Okay. So how are alpha 1 and alpha 2 related? They sum to 1. One of them is 0, so the other one is 1. So you get both the, yes, conditions on the kinematics. You see, these are, at least to the first instance, these are conditions on the kinematics. When this object that depends on P, M1 and M2, has this relation among the three variables, then the integral will become singular, or it might become singular. All right, are we done? What do you guys think? Well, what do you think?
Yes.
Excellent. Well, that's what like physicists thought for like a long time, and Landau himself had not noticed. And it was later that Katkovsky noticed that there is also yet another subtle solution. So subtle, there is also a subtle case. It's because it's a limiting solution. It's a solution where you have to take a limit to get it. That's why it was overlooked. And let's see, what should I say? Since it's well, I can give you the basic, and we can come back to it next time. But you pick a reference frame. Pick a reference frame such that K and P are on the same plane. So K is K0, 0, 0, K3, and P is again P0, P3. Then if you try to solve the equations, so yes, equation 1 for alpha I different from 0, you can write them as, okay, the first equation is k squared equals k0 square minus k3 square equals m1 square. And this geometrically, one can see geometrically that is a rectangular parabola. Hyperbola. Rectangular means that, normally there is, I don't know, x over x square over x square minus y over b square. In this case, a and b are the same. So it's rectangular. And similarly, k minus p squared equals m2 squared. This is same, but with shifted center, with center shifted by p. So that's the first equation, the first set, the equations 1, the set of both equations 1. And then the second equations, alpha k mu plus 1 minus alpha k minus p mu equals 0. And this means that k mu is 1 minus alpha p mu, so it's collinear, so the vectors are parallel. That's the, like, again, geometric origin of the second equation. Well, if we draw these, let's take this to be, let's make this, okay, so this is the purple one, and so on. So this is one parabola. Let's with center here. And the other one should have a center that is shifted. Let's say that. So this is P. And so this is another parabola that is also. And this, so these are two parabolas, the centers are shifted. The second equation is that, okay, so we are looking for one particular point in each of these parabolas where the vector k, so you know, k could be, this is for this particular point, this is k nu at this particular point, and then this is k mu of the other parabola. So do you see where could have that these sets of equations could have a common solution? Namely, is there a point on these parabolas where k and p become parallel? No one sees this? Okay, let me ask. If we take, so this is our equation for the parabola, let's solve it for k0. K0 is m1 squared square root, m1 squared plus k3 squared. Let me take k3 to infinity. What happens to k nu? Is it does it become roughly like space like? Yes. K0. Okay, yes, very good, very good. So K0 is square root K3 square plus M1 square, So if you take K3 to infinity, this becomes K3. So therefore K nu is what? Light like. Very good. Okay. And obviously the same for the other parabola, right? Nothing. What a rectangular parabola means that it goes off to infinity at 45 degrees. Therefore, if also P is light-like, there is a solution to the system. But it happens when K is infinity, and it's possible to show also that alpha has to be infinity. That's why it's a solution that was overlooked. One should have kind no, when you are solving equations, it doesn't matter. You are solving them everywhere, over the entire, complex plane. So this is the so-called second type 2 singularity. In the beginning, it was called non-Landauan, but it's type 2 singularity. And it was initially overlooked. And you see that these equations, while in principle contain everything, they are written in a way that is very simple. It is often likely to miss solutions. You have to be very careful with, there is no systematic in finding these limiting solutions. Here one should take, K3 to be finite but large, and then take the K3 to infinity limit to find the solution. So that's why this topic is very, very active nowadays. So let me close. Let's see how we are doing on time. Okay, no, I'm over time. This is a very, very active topic precisely for these reasons, because the Landau equations are very hard to solve. We might miss singularities, and these are also needed to actually directly evaluate the integrals. They play a central role in able to directly evaluate the integrals, and this is what we'll talk about next time, how to use this information to directly evaluate the integrals. Thanks a lot for your attention.